Hello, my name is Duarte, and I will be talking about my poster about simulations of atmospheric pressure microplasma jet flows using Spark. These simulations will be done in accordance with our reactor, which is a coaxial reactor. Basically, we have an argon gas, and then we change the co-flow gas so that we can change the shielding around the argon jet. And so our geometry for our simulations will follow more or less here what you see here. We are using Spark, which stands for Software Platform for Thermodynamics Radiation Kinetics. This is a code that has been used mostly for hypersonic reentry plasmas, and we adapted it to subsonic and low temperature flow conditions. I have here an example of our first simulations, and then after our changes we were able to increase the fidelity and the cell count and also increase the computational efficiency. After these improvements we did some perfect gas simulations, and we have some results which compare pretty well with our Schlieren experiments. Namely, we have a diffuse jet at a low flow rate, and then when we increase the flow rate we start to have a longer, narrower jet until we have an unstable jet. We also did some multi-component simulations. Here we are trying to mimic our co-flow reactor, so we are changing also the shielding gas. For some of the results here, I also compare with different inlet profiles. I'm using a top hat profile or a parabolic profile, and we see some differences in the argon mass fraction. Namely, top hat leads to a higher mass fraction along the center line. Also, for the case of varying gas mixtures, we see for 100% nitrogen we have a higher argon mass fraction along the center line than for 100% oxygen, and I think this is related also with the viscosity of oxygen being higher, which increases the mixing with the argon. Here we also have some tests that we did with electron energy source terms, and this is how we are going to include the plasma in our jet simulations. This is just a simple test case. We are placing some power density here. We are increasing a lot the electron temperature, which then excites metastable states that then decay. Furthermore, when we take out our power source, we also have some evolution of the radiative states, and we have the evolution of the charged species. We have some problems here with the loss of charged species and with the decay times of the metastables, but I believe this is a good starting point so that we can then include these electron energy source terms in our argon jet simulations. So this is my poster, and thank you for watching. I hope we can talk a bit more later on. Thank you.